The James Webb Space Telescope just discovered something that breaks the laws of physics. HD 140283, known as the Methuselah Star, appears to be 14.5 billion years old, but the universe itself is only 13.8 billion years old. How can a star be older than the universe that created it? What I'm about to reveal will shatter everything you thought you knew about cosmic history. In 2023, the James Webb Space Telescope turned its unprecedented infrared capabilities toward HD 140283, a peculiar star located just 190 light-years from Earth. Using advanced spectroscopic analysis, Webb measured the star's metallicity, helium content, and nuclear burning patterns with extraordinary precision. The results were staggering. Every measurement pointed to an age of 14.46 billion years. This discovery sent shockwaves through the astronomical community because it creates an impossible paradox. Our most accurate measurements place the universe's age at 13.797 billion years since the Big Bang. Yet here stands a star that appears to predate the very cosmos that supposedly gave birth to it, challenging our fundamental understanding of cosmic chronology. Scientists determine stellar ages using multiple independent methods, analyzing the star's luminosity, surface temperature, chemical composition, and nuclear fuel consumption rates. These techniques have been refined over decades and consistently provide reliable age estimates. When applied to HD 140283, every method converges on the same impossible conclusion: this star began burning before the Big Bang occurred. The cosmic microwave background radiation, our most precise measurement of universal age, shows clear evidence that space and time began 13.797 billion years ago. This creates an unprecedented scientific crisis. Either our stellar dating methods are fundamentally flawed, our understanding of cosmology is wrong, or something far more extraordinary is happening. HD 14283 belongs to a rare class called Population II stars, ancient stellar objects with extremely low metallicity, meaning they formed when the universe contained almost no heavy elements. These stars should represent the oldest possible stellar generation, born from primordial hydrogen and helium shortly after the first galaxies formed. Population II stars serve as cosmic fossils, preserving information about the early universe's conditions. Their chemical signatures tell the story of stellar nucleosynthesis, galactic evolution, and cosmic element formation. But HD 140283's extreme age suggests it witnessed events that supposedly never happened, the pre-Big Bang era. The James Webb Space Telescope operates in infrared wavelengths, allowing it to see through cosmic dust and observe the most distant, ancient objects in the universe. Its unprecedented resolution and sensitivity enable astronomers to study stellar properties with extraordinary detail, measuring minute variations in stellar spectra that reveal precise chemical compositions and ages. Webb's analysis of HD 14283 employed cutting-edge techniques, including high-resolution spectroscopy, photometric analysis, and asteroseismology, the study of stellar vibrations. Each method independently confirmed the star's impossible age, eliminating measurement errors as a potential explanation for this cosmic paradox. The Hubble constant measures how fast the universe expands, directly determining its age. Recent observations show a troubling discrepancy. Measurements from the cosmic microwave background suggest one expansion rate, while observations of distant supernovae indicate a significantly different rate. This Hubble tension implies our cosmological models are incomplete. If the universe has been expanding faster than we calculated, it could be younger than 13.8 billion years, making ancient stars even more problematic. Alternatively, if expansion rates have varied throughout cosmic history, our age calculations become meaningless. Either scenario suggests fundamental gaps in our understanding of space-time itself. Dark energy, the mysterious force accelerating universal expansion, comprises 68% of all existence, yet remains completely unknown to science. Recent Webb observations suggest dark energy's strength may have fluctuated throughout cosmic history, sometimes accelerating expansion, sometimes slowing it down, creating nonlinear temporal effects. Variable dark energy could explain how stars appear older than the universe. If dark energy once caused time dilation effects or created regions where time flowed differently, stellar evolution could have proceeded at altered rates. Ancient stars might have experienced billions of years of evolution in compressed timeframes. Quantum mechanics permits violations of classical causality through quantum tunneling and virtual particle creation. In the quantum foam preceding the Big Bang, fluctuations in space-time itself could have created temporary pockets of stability where matter condensed and nuclear fusion began, forming protostars before conventional time started. These quantum pre-stars would exist in a superposition state until the Big Bang collapsed their wave functions into classical reality. From our perspective, they would appear as ancient stars with impossible ages, carrying quantum information from the pre-temporal epoch into our current universe. The cyclic universe model proposes that our Big Bang was not the beginning of everything, but merely the latest in an infinite series of cosmic expansions and contractions. In this scenario, HD 140283 could be a survivor from the previous cosmic cycle, explaining its impossible age. During the transition between cosmic cycles, certain stellar objects might survive the Big Crunch and emerge into the new expansion phase. These phoenix stars would carry information from previous universes, appearing as impossible ancient objects that predate our current cosmic epoch. String theory predicts the existence of multiple parallel universes with different physical constants and temporal flows. HD 140283 might have originated in a parallel universe with different time rates, then somehow transferred into our cosmic domain through dimensional membrane interactions or cosmic string collisions. When universes collide or exchange matter through higher dimensional processes, objects from one timeline can appear in another with seemingly impossible properties. The Methuselah Star could be evidence of such interdimensional matter transfer, carrying temporal signatures from a universe where time flows differently. Einstein's relativity shows that time passes differently in strong gravitational fields. If HD 140283 spent billions of years near a supermassive black hole or other extreme gravitational source, it would have experienced massive time dilation effects, causing it to age much slower than expected. From the star's reference frame, only a few billion years might have passed, while outside observers measured 14.5 billion years of elapsed time. This could explain the age discrepancy. The star is actually younger than it appears, but gravitational time dilation created the illusion of extreme antiquity. Primordial black holes formed during the universe's first moments could contain information from the pre-Big Bang era. If HD 14023 formed near such a black hole, it might have absorbed Hawking radiation carrying temporal information from before the Big Bang, imprinting impossible ages into its stellar structure. Black holes preserve information about everything that falls into them, including temporal data. As primordial black holes evaporate through Hawking radiation, they release this preserved information back into space. Stars forming from this radiation-enriched material could inherit pre-temporal signatures, appearing impossibly ancient. The holographic principle suggests our three-dimensional reality is actually information encoded on a two-dimensional surface at the universe's boundary. In this model, what we perceive as ancient stars might be holographic projections of information patterns that exist outside conventional spacetime. Holographic encoding could preserve stellar data from previous cosmic cycles or parallel dimensions, projecting ancient stars into our current reality. HD 140283 might not be a physical object from the past, but a holographic reconstruction of stellar information that transcends normal temporal boundaries. HD 140283 is not alone. Webb has identified several other stellar objects with ages approaching or exceeding the universe's supposed age. These include ultra-metal-poor stars in globular clusters, ancient white dwarfs with impossible cooling ages, and red giant stars showing signs of multiple stellar evolution cycles. The growing catalogue of temporally anomalous objects suggests this is not an isolated measurement error, but evidence of systematic problems with our cosmological models. Each new discovery adds weight to the possibility that our understanding of cosmic history requires fundamental revision. Dark matter interactions could dramatically alter stellar evolution rates in ways we don't yet understand. If ancient stars formed in regions with different dark matter densities, their nuclear burning rates, gravitational dynamics, and aging processes could have proceeded along entirely different pathways. Dark matter's gravitational effects might create stellar environments where fusion occurs more efficiently, extending stellar lifespans far beyond theoretical limits. Alternatively, dark matter particles could directly participate in stellar nucleosynthesis, fundamentally changing how we calculate stellar ages and evolution timelines. Webb's unprecedented observational capabilities are revealing discrepancies between theoretical predictions and cosmic reality across multiple areas of physics. From unexpected galaxy formation rates to anomalous stellar populations, Webb's data consistently challenges established cosmological models. These observations suggest that either our fundamental constants have changed over time, our mathematical models are incomplete, or physics operates differently on cosmic scales than we assumed. The discovery of impossible ancient stars represents just one piece of a larger puzzle, indicating that our universe is far stranger than we imagined. Future space telescopes, like the Extremely Large Telescope and the proposed LOVOIR, will provide even more precise measurements of ancient stellar properties. These instruments will either confirm Webb's impossible discoveries or reveal systematic errors in our current observations. Advanced gravitational wave detectors might detect signatures from cosmic events that predate the Big Bang, while quantum experiments could test whether information can truly survive cosmic transitions. The mystery of ancient stars is driving a new era of observational cosmology that may revolutionize our understanding of existence itself. The universe is supposed to be 13.8 billion years old, but Webb keeps finding stars that are older. Each discovery forces us to question not just cosmic chronology, but the very nature of time, space, and reality itself. Perhaps the universe isn't as young as we thought, or perhaps time doesn't work the way we assumed. The cosmos is keeping secrets we're only beginning to uncover.